Hi, I'm Mike Thompson. Welcome to more rocket science. In this video, we're going to design and build a rocket from scratch. Well, not entirely scratch, of course. We've got motors and things that are pre-made for us, luckily. We don't have to make our own motors. We may not have to make our own tubes, depending on what we have lying around. And some of the other stuff, like nose cones and things, we may make that. But the point of this video is to show you how it all now comes together. We're going to design, we're going to tabulate everything, and we're going to ensure that our rocket's going to fly before we actually fly it. And then, of course, we're going to fly it. So to get started, we have, of course, some couple key components. One of which is a motor. We need some sort of body tube. We need some sort of fins. And we need some sort of nose cone. And that's basically it. You got those four basic parts, with plus or minus a few others. Now, the first thing, of course, is to start thinking about what size of rocket and things that you want to make. Well, that kind of is dictated by the size of the motor that you have. For this example, let's use, say, a C65 by Estes. Standard little low-powered rocketry motor. Okay, so you've got this. We can't make this, so this is our design constraint. We're going to use one of these. We got a C65. Now, you may have a couple tubes lying around the house. Let me stop you right there. Mailing tubes are horrible for low-power rocketry and simply aren't going to work because the wall thickness is way too thick, which means the tube is far too heavy. So these here simply aren't going to work. You may be tempted, but please stay away from those. This one here has a thinner tube, but it's still far too heavy for our relatively puny C65. Now, one thing you might have lying around, especially this time of year, is wrapping paper. You're about to have gobs of wrapping paper, I bet. I know I will. There's some left over here from last year or the year before. But the tube inside this is relatively straight. It's light. And I think it'll work just fine. The reason that this is going to work over something like this is the size of the wall. The wall thickness is much thinner for this because this wrapping tube is not made to take any lateral crushing load like a shipping tube is. So therefore the wall is much thinner. We generally only have to deal with compression and a little bit of bending. And a tube such as this will work just fine. Now, you may also, if you don't have any tubes lying around, this one here would work as well. This one here would probably work too. This clear thing would be pretty cool, but not for our C65 rocket. What you might have to do is, like one of the other videos I showed you, get a dowel rod or some sort of other mandrel and make your own spiral wound tube. Go check out that video if that's something you're interested in doing. For this video, we're going to just pick a tube that is going to probably work. Now, once we've decided on our tube, the wrapping paper, we're going to have to get this out actually. So what I'm going to do is transfer this wrapping paper to this dowel rod for the moment. Bear with me, please, while I do that. Okay, so we've got our basic components listed. Now we need to tabulate these so that we know how this is all going to shake out when we go to calculate the center of gravity and the center of pressure. I've got my little food scale here. This goes up to 11 pounds. It's fairly common. I'm going to put it, though, in metric because at roughly 30 grams to an ounce, I have better resolution if I do this in grams than 1/8 of an ounce, which is as best I can get in US units. So I'm going to put that there in, so I'm going to put it in grams and zero that out. And what I'm going to do is weigh all of my key components. So that way, when I go to calculate the CG, I'll know where that's going to be. So I'm going to look at all the candidate tubes that I think I might use, and I'm going to weigh them, and I'm going to measure them. We're going to measure the key weights and dimensions for each of our primary objects, which we have 4. So we're going to do this guy here. This tube is 56 grams. So I'm just going to write that right on the tube for this case because I don't really care. We end up painting this later. 56 grams. It's actually 29.4 grams per ounce, but 30 is a good rule of thumb. This little shorter tube here is a whopping 18 grams. Now, in addition to weighing all of our candidate parts, we need to measure them so that we can then go and calculate the CG and CP, because the CP is dependent upon the area of the object and the CG is dependent on lengths and things. So I'm also then going to measure each of these, and then I'm just going to write it right on there, and then we'll put that in our table. This guy here is 12 1/16. Our C65 motor is 24 grams. This tube is 12 1/16. This is 10154, looks about. Now these, I'm going to average 10 of them because I only have 1 gram resolution. So we'll stack 10 of these on here, and we'll find out they're 4.6 grams apiece. And this motor, center of gravity is right there, 1.52. Let's go to the computer, or the whiteboard actually maybe, or let's do it in the computer. Excel is great for something like this because you can easily manipulate your numbers and get a rocket that's going to work rather than have to go back and rework all the problems. So let's get all this stuff weighed that we think we're going to use and measure everything and go stick it over in the table. Alright, so the major items to consider are these 4 here. The body tube, the motor, the nose cone, and the fins. Minor items, of course, here are launch lugs, motor mount, and the recovery device. And so I've got this spreadsheet set up here with all the different material properties down here for each of the things that I just measured. Things like body tube weight. I've got the 3 different tubes, so I've got options 1, 2, and 3. I've got the lengths, the CG location of each. Of course, these tubes are homogeneous, so the CG location is just right in the middle. I've got my 3 tube. This one's 18 grams. Now notice I'm using grams and inches. Doesn't matter that I'm mixing SI units and English units. This is what I had available, and so it'll work out just fine, as long as I keep everything consistent. And see here, the CG is just length over 2, because it's all a homogeneous tube. Just like so, B19 over 2, and then we just drag this formula over for the other 2 tubes. Oops, nope. Alright, so down here, I weighed my motor, and the C65 was 24 grams. It was 2.75 inches long, 0.7 in diameter, and its CG was 1.52, measured from the front of the motor. I want to measure everything from the front, so I'm just keeping it consistent. Now the fins were 4 inches in diameter, or the fin material rather, and this gave me a specific weight of 0.36 grams per square inch. My recovery device, I'm estimating here at 5 grams, and it's going to be about 1 inch behind my datum. Now over here is where I'm actually going to design the first version of this. I'm choosing the front of the body tube to be my datum because I don't have my nose cone yet, and so I'm going to use this. This is a hard limit. I'm going to do this first with the 18 gram tube, which is option 3 from over here. I'm going to basically copy those numbers there over into my design alpha for the weight, the length, the diameter here, 1.08, the CG of the tube. Now its projected area, of course, here is its diameter times its length. You can see that it's I7 times I8. The great thing about the computer is you can change one little thing and you don't have to go redo it all. So that's why I do this in Excel. The mass moment was the weight times its CG location, and the area moment is the area, so length, diameter, times the CG location, which was the centroid of our shape in this case. It's called CG up there in the purple cell, but disregard that, it's the centroid. So now we come down here to our nose cone, which I designed a custom one in SolidWorks, but you can, if you've seen my other video, you can use a Tootsie Roll for a nose cone, for all I care. But it calculated my area for me, and the centroid of the cross-section was at minus 0.78. Now these are negative numbers because the nose cone is ahead of my datum at the body tube. So these are negative numbers. And this is very important that you keep the signs correct. And I wanted to choose my datum to be where it is so that you can see that sometimes you'll have negative numbers in your calculation and it's going to work out fine. Of course, the nose mass moment here is I14 times I18. It's the width times its location, and the area moment is its cross-sectional area times its centroid. And it's a funny kind of shape, so it was nice to have the computer calculate it for me. Negative numbers are just fine in a calculation as long as you do everything correctly. Now, I drop down here to my motor section, and I'm going to play with this green number here, the motor position, because this allows me to change the CG. This is measured from the datum to the front of the motor, which is where I chose to measure from. Right now, I've got the motor set up to be flush with the back of the body tube. and that's 9.31 inches. The center of gravity with relationship to the rocket, of course, is the datum position times the CG, which gives me this number here at 10.83 inches. We go and sum all this up, sum of the moments over the sum of the masses. For the body tube and the motor at least, my motor mass moment is 259.98. I've got 8.77 BT motor and CG. Now this number is pretty well meaningless, especially these down here. I just calculated them for curiosity, just to kind of see what was what, how much of my CG was ahead of my, how much of my tube was ahead of my CG and how much was behind. Don't pay attention to the tube A and tube B behind things. Now, my fin-specific weight. Remember I calculated that area. Varying the fin area and position are the two key variables that you can use to change the center of pressure. I've got pi over 4 d squared to calculate the area of one of those coasters that I'm going to be using. And so that's 6.28 because I'm only using half of it for a single fin. The center of this, of course, in the longitudinal direction is 2 inches, and I'm going to use 4 fins, I think. It's going to be a nice round calculation for now, so we'll stick with 4. And like I said, these green cells are the ones that I can change. I can change the size of the fin easily, and I can change the count easily. So the projected area of one of these is, of course, one coaster, if I'm looking at it on the side, which is 12.5 square inches. Fin position is an easy thing I can play with. Right now I've got the fins positioned so that the back of the fin is flush with the back of the body tube, and we'll see how all this shakes out. We've got the centroids, the mass moments, and the area moments. Of course, anytime I change the fin sizes or move the fin position, it's going to affect the CG and the CP. You can see here the area moments calculated quite easily. Now these are only going to be good for the 4-fin rocket. Don't just use this spreadsheet that I'm going to make available as is. You need to think this through on your own, but this will get you a good start. And so, the nose, the recovery system, body tube, motor, and fins. Sum of the moments over sum of all the masses gives me 7.44 inches. The nose, body tube, motor, fin CP is 7.5 inches. These numbers are basically right on top of each other, which means I really don't have stability. I mean, we are right on, marginal stability here. And so we need to do some stuff to change this. And so I'm going to do that. I would like to get this, remember, at least one body tube ahead. The CG needs to be at least one body tube width ahead of the CP. So we're about an inch. We need an inch spacing between these two. So I'm going to change the fin position. Instead of having the backs of the fins flush with the back of the rocket, let's move them back. Let's say we add an inch maybe. Or let's move the motor first. Let's move the motor inside the tube. We'll move the motor forward. Because, I mean, you got this big heavy thing at the back of the rocket. It's horrible for CG. Ideally, you'd have your motor at the very front of the rocket, but of course, that presents other challenges. So let's do this. Let's take this motor and let's bump it forward maybe a little bit. I'm scrolling here randomly. So we need to pay attention. That's 7.44 and 7.5. 7.44 and 7.5. Let's move this up an inch. So it's going to be an inch closer, or half an inch, excuse me. Move it up half an inch. Okay, and so now it's at 8.81. And let's see what our new numbers are down here. Okay, well now I've got a 1/4 inch spacing. Well, that's a quarter of what I need, so we got to do something else. So let's move that motor a little bit farther inside the tube. Can't move it too far because the exhaust plume, will hit the side walls of our body tube. So let's go 0.75, I think will be fine. Can't go much more than that, really, for a tube this size. The wider the body tube, of course, the farther you can put your motor inside the tube and not have the exhaust hit the tube. Now we're at 8.56, and every time I move this, the CG is changing, but the CP is not, because this is an internal thing. So now we got 0.35 inches. We're a third of the way there. We need at least 1.08, really, for me to feel comfortable. So we've done about all we can with the motor, and the fin size is fixed because I want a fin that's a semicircle made out of these, so I can move the fins. That's my only option. So let's move them back. Let's move them an inch for starters. So it's going to get farther away, so this distance is increasing, so it's +1. And we'll see what's happened here. You saw the centroid move. There, it's 11.06 now. This moved the CG and the CP. We're getting close. We got about 3/4 of an inch spacing now, more or less. but it's not quite enough. So let's move it back another inch. Let's go so +2. Okay. 8 point, look at that. All right, that's good. We've got a 1.02 inch spacing. I'm okay with that. And we didn't add any weight to this. Yay. So this rocket's going to be stable. I like that. And you can see how easy this was by using Excel. Didn't have to go recalculate anything by hand. Just move some stuff around and you can do it very, very easily. Let me bump my recovery system weight up a little bit here, and you can see that this will move my CG a little farther forward. I'm going to add 3 grams. I know I don't like adding weight, but you can see how this affects this. And now that bumps my, look at that. By adding 3 grams, I got an extra 0.3, essentially. 0.3 inches on my CG. Anything, of course, inside the rocket will affect your CG, and it will not affect your CP because it's inside. Anything outside will affect both when you move them. And our total mass here is 65 grams and 2.2 ounces, give or take. Now I've still got to add some paint. I need to add launch lugs and a motor mount and account for that. But those are going to be very minor. But if you really want to get this down, I'll show you later, you need to add those. So we'll cut this coaster here in half, and I'm going to build it to spec, as I just calculated. So these are going to be my 4 fins. Let's make 2 orange and 2 blue, so it's easy to see. This thing needs to be easy to see because this rocket's fairly small. Here's my 3D printed nose cone that I made, tied a knot in a rubber band, and threaded it through there. A little bit of electrical tape, and this will hold this shock cord inside the body tube. You can see how this is all I didn't use really anything special other than the 3D printed nose cone, which doesn't look all that good. Now I'm going to custom make motor mounts here. You've probably seen a video about me wrapping stuff, and here I am doing it just now. I'm using a motor and wrapping multiple layers of glue-sticked paper around it to build up enough thickness to center this motor inside the body tube. Separate it like so with this knife, make a couple little rings here. I'm going to just make 2 little thin rings to center it. I made more here than I really need, which is good. And so this, I've poked 2 little holes in for a paper clip. It's going to go through there, and this is going to stop the motor from shooting up inside the body tube. That's going to apply the thrust. And these 2 little rings, that's going to go like that. I've bent this paper clip to make a hook here for the engine, just like so. I love bending paper clips. I hardly ever use them to clip paper. That's going to go up in there like so. Shove it in there with a little bit of glue on it, and that'll be good. And then I need to set my calipers, remember, to 0.75 inches because the end of this motor is no longer going to be flush with the back of the body tube. It's going to be 3/4 of an inch up inside. All right, and I've used my folded paper trick to position my fins here, and now I'm making sure that they're just coplanar, because obviously you want 4 fins to be coplanar with their opposing mate. There, you can see it there better. I had to shim this up a little bit, and then that one there, and then I need to make sure it's square here. So I'm just going to let this sit here while that fin cures. Just regular wood glue. And then sight down the top one here, and you can see that one looks straight as well. Done. And then I just built a parachute out of some plastic trash bag and some cotton, I think it was crochet thread. But I couldn't get it to weigh 8 grams like I needed. My CG came out to be right here, which is 7.5 from the front of the body tube, which is nearly where I was hoping it would be, and the twirl test to confirm that this all is work. And you can see here that my CG didn't come out to be exactly where I computed it to be. It was within 1/8 of an inch because I just couldn't get my recovery device to be 8 grams. 8 grams for a recovery system for this rocket would be really, really heavy. But as you can see in the twirl test, it all worked out fine. And 1/8 of an inch is awesome. Let's get to it. Alex, you ready?
Yeah.
All right. Systems armed. Three, 2, 1.